Thank you for the introduction. Today I'm going to present our work, learning implicit topology for CNN-based aortic landmark localization, short as LitCall. So I'd like to first give some introduction about what is aorta. So it's the largest artery in the body, and it carries blood from the heart to the rest of the body. So CT is the most common way imaging aorta, and we also use CT in this work. So aorta can extend longitudinally from the chest to the abdominal cavity. And this work only focuses on the thoracic aorta, which mainly consists of three parts: ascending aorta, arch, and descending aorta. So why are those landmarks useful, or why do we want to detect the aortic landmarks? So in the clinical practice, one essential task is to measure the aortic aneurysm growth over time. But as this picture shows, traditionally, radiologists will first define few locations and take a CT image to some software like ITK-Snap to manually adjust the plane and draw the line to measure the diameter or draw the boundary to measure the area. So you can see this approach is very time-consuming, and more importantly, it introduced lots of greater variability. But with this landmark localization technique, we can do it automatically and provide consistent measurement over time. So our goal is, given a CT image, we want to locate 4 landmarks on the aorta, labeled from L1 to L4. So L1 is on the root of ascending aorta. L2 and L3 are on the arch of the aorta, at the intersection point between the main vascular and the artery. And L4 is at the corner between the descending aorta and cilia. So here I visualize 5 3D aorta surfaces. The inspiration of this proposed method comes from this observation, that despite the differences in size, shape, tortuosity between individuals, the landmarks have relatively stable topology. So this becomes more clear when I label this out. So you can see the topology all are different, and they all look like a question mark or a candy cane. So now you have seen 5 different aortas in your life, and I assume you didn't see any before. But I believe you can also solve these 2 quizzes very easily. So it says, given the information below, can you estimate the location of the missing landmarks? So for example, in the quiz 1, L1, L2, L3 are given, L4 is missing. And in quiz 2, L2 to L4 are given, L1 is missing. So I will give a couple of seconds and a little bit of hints that those 2 quizzes have some symmetry between them. Okay, so if your answer lies around the blue region, then congrats, you're correct. So now we have seen how quickly humans can capture this topology. What if we let the computer learn to solve this quiz? Will it learn any useful knowledge? So here we have a CT dataset, and the landmarks are labeled in a CT image. The algorithm is trained to predict the location, just as humans trained to do that job. And for the quiz part, given a few landmarks, not all of them, the algorithm also wants to estimate the location of the missing landmarks. So here, the landmarks are represented in the 3D heat map, with the largest value being the location of the landmark. But here we model this as an auxiliary task, and we hope this algorithm can learn the topology, which could be helpful to a localization task. So this is how our model looks like. We first use 3D Unet to predict for 3D heat map. Each heat map corresponds to a landmark. A larger value in the map indicates a more probable location. And for the supervision signal, given the ground truth coordinates, we generate 4 heat maps with a Gaussian kernel. And then we compute an MSE loss between the predicted map and the ground truth map. So we call this loss as a regression loss. So by far, this is a very standard framework for regressing the heat map to locate the landmarks. And then we introduce a selection module that randomly selects several subsets of landmarks. So you can see for some subsets, we give three visible heat map, and for some subsets, we only give one visible map. And we use a lightweight head to predict the location of the missing landmarks. And this head only contains about 0.4 millimeter parameters. Then we compute another MSE loss between the ground truth and the predicted missing map. And we call it implicit topology loss. Meaning by minimizing this loss, we expect the network to learn the underlying topology. And here is our total loss used for training. So during the training, the gradient will start from the loss and backpropagate to the backbone to update the parameters. And note here we set the sigmas to be a learnable parameter. And these sigmas control the size of the Gaussian kernel. A larger sigma gives you a larger blob, while a smaller sigma gives you a spike in the heat map. And most previous work used a fixed sigma to generate the ground truth map, and fix that during the whole training process. However, if you choose a larger sigma, the width of the Gaussian kernel is large, so the localization might not be very accurate. Generally speaking, smaller sigma looks more focused and concentrated and accurate. However, if you use a too smaller sigma, it seems to provide a very small region as supervision. Thus leads to a very small gradient, which is bad for training. So this is why we design the sigmas as a learnable parameters. So here's what we do. We initialize with a moderate sigma, like 10 voxel, and let the learning process to decide when and how to decrease the sigma. So during the inference, we just take the backbone and feed forward the image to get the heat maps and find the maximum value and pick its location as the final landmark location. So here's the data we used. We used 207 thoracic CTA. The average size, volume size is such log, and here's the resolution. And we use 80/20 split for training and evaluation, and it takes about a day to train the whole model. So here are some quantitative results. The Euclidean error between the predicted location and the ground truth used as a metric. And we use 3 backbone as a baseline: the Unet, ResUnet, and the UnetR. Since we also use a lightweight head to do the auxiliary task during the training, so our model has 0.4 million parameters more than the baseline model. So we increase the number of channels of the baseline as another stronger baseline. And we name those models as Unet/L or ResNet/L. So that we can confidently say that by comparing those numbers, we can say, well, our better performance comes from our lead module instead of just using more parameters. So here it shows the cumulative landmark localization error. So X represents the Euclidean error, and Y represents the percent of the landmark. So the larger area under the curve indicates a better performance. And different color labels different backbone. Solid line indicates the baseline, and the dotted line indicates the model where our lead module is applied. So as you can see, the solid line is always better than the dotted line. So that says by integrating with lead module, the landmark localization accuracy gets improved for all 3 backbones. So here are some qualitative results. Sagittal, coronal, axial slices are shown here. And we pick up the ResUnet and ResUnet plus lead as an example. So in this case, ResUnet wrongly locates the L3, the 3rd landmark, at the other side of the artery, as shown in green cross. And in this case, the ResUnet wrongly locates the L4 at the 2nd cilia instead of the 1st one. So in summary, we propose a landmark localization network which improves the localization accuracy by learning the implicit topology among the landmarks. And the method is plug and play for widely used Unet variants and backbone. So now, what can we do with this technique? We believe it can be helpful in two applications. First, when you know where are those landmarks, you can divide the aorta into different segments, ascending, arch, and descending, as shown here. If your previous work, for example, analyze some deformation or vascular tension for an aorta as a whole, now you can group your metric in a segment basis, which will provide a more finer level analysis. And another application we could do is to automate the centerline generation. Once you got L1 and L4, you can do that automatically using some open source toolkits such as VMPK, which is an open source Python package. Also, going forward, it will greatly help the traditional way of measuring the growth of aortic aneurysm. So for conventional metrics such as the diameter, area, and volume, people won't need to manually locate the plane and draw the line to do the measurement. Thus, the variability is reduced. With this technique, those metrics can be measured in a consistent and automatic way. So in addition, our lab also developed an image registration-based method that maps the deformation onto the surface, which provides growth measurement for each voxel. Based on that, we explored the possibility to decouple 3D deformation into the stretching in the longitudinal direction and the expansion or contraction in the radial direction or the cross-sectional direction. However, previously we can only do this by providing the technique, the centerline. But now, combined with our LIT module, which provides the landmarks, we can perform the whole directional analysis automatically. So combined with those techniques, we can automatically generate some description or give some description like this. Patient A's descending aorta has expanded 20 millimeter cubic over the past 3 years, and the deformation is mainly in longitudinal direction. So we can tell descending aorta because LitCall divides the aorta into separate parts, and we know it's in the descending aorta. And we can measure the growth by calculating the volume change. And the directional analysis tells us the deformation is mainly longitudinal instead of the cross-sectional change. So finally, we plan to apply LitCall to other modalities or tasks, such as localizing the hand joints through X-ray or vertebrae joints through CT. And here are some closely relevant work. And thank you. I'm happy to take some